All right, we're continuing with errors again. This is the last section. I believe it's 9.3. Let's look at it again. 9.3. To panic or not to panic? That is the question. So, the first word is so. Okay. So how do you decide when you should call panic and when you should return result? When code panics, there is no way to recover. You could call panic for any error situation, whether there's a possible way to recover or not, but then you're making the decision on behalf of the code calling your code that a situation is unrecoverable. When you choose to return a result value, you give the calling code options rather than making the decision for it. The calling code could choose to attempt to recover in a way that's appropriate for its situation, or it could decide that an error value, in this case, is unrecoverable. So it can call panic and turn your recoverable error into an unrecoverable one. Therefore, returning result is a good default choice when you're defining a function that might fail. Alright, so in summary, what they said there was that we know that there are two options in terms of errors. There are recoverable ones and unrecoverable ones. If I write a function, right? And let's say you want to call my function or use my function. I have the option of returning recoverable or unrecoverable. If I return a recoverable error, then I'm allowing your code that's calling and using my code the option of choosing how they deal with the errors I return, or how they deal with this error case in general. However, if I panic within my code and you're using my code, I have taken away that option for you, and I have let you know, well, I've taken away that option for you, and there's nothing you can do about it. So in terms of being generous to other people and other programmers and other code in general, other code out there, they're saying the default should be to return a result. In rare situations, it is more appropriate to write code that panics instead of returning a result. Let's explore why it's appropriate to panic in examples, prototype code, and test. Then we'll discuss situations in which the compiler can't tell that failure is impossible, and you as a human can. The chapter will conclude with some general guidelines on how to decide whether to panic in library code. Alright, so let's see what they are talking about here. So examples, prototype code, and test. When you're writing an example to illustrate some concept, having robust error handling code in the example as well can make the example less clear. In examples, it's understood that a call to a method like unwrap that could panic is meant as a placeholder for the way you'd want your application to handle errors, which can differ based on what the rest of your code is doing. Similarly, the unwrap and expect methods are very handy when prototyping before you're ready to decide on how to handle the errors. They leave clear markers in your code for when you're ready to make your program more robust. If a method call fails in a test, you want the whole method to fail, even if the method isn't the functionality under test, because panic is how a test is marked as a failure. Calling unwrap or expect is exactly what should happen. Alright, so they're going over 3 different examples, which is kind of ironic because technically speaking, I don't think we went over tests. Tests might be like a chapter or 2 away. Let me check. Yeah, testing is 2 chapters away. Thank you, but at the same time, we haven't gone over testing yet, so that's kind of irrelevant. But back to what they are trying to say. So here they're going over the 3 examples that they mentioned where it's okay to not handle your errors explicitly, seemingly. So in examples, right, the first one they mentioned. If you're writing an example, you're trying to illustrate some concept and you're trying to get your point across. If you had robust error handling within that code, that could distract the reader from the point that you're trying to illustrate. Thus, it is okay to use unwrap and panic as willy-nilly, pretty much. So in the second paragraph, they were going over prototyping code. So prototyping is a special situation because, yes, you're writing code, you have a general idea of what you want to accomplish, but you don't have all the answers to the questions that you may have. For example, there could be a question of, how should I handle this error? How should I handle that error? instead of trying to figure out what those answers are immediately, because you don't know if this code is going to be useful or not, you're just prototyping, you could use the unwrap and expect as place markers, so that when you finish prototyping and you have to come back and make a final product, you can go to these place markers, unwrap and expect, and fill out the robust error handling and deal with everything as you should. And the next part that they went over, which is sort of ironic because we haven't gone over testing yet, is testing. And apparently, calling a panic is how a test is marked as a failure. Thus, you should call panic. And thus, calling unwrap or expect is exactly what should happen. Okay. Cases in which you have more information than the compiler. It would also be appropriate to call unwrap when you have some other logic that ensures the result will have an okay value, but the logic isn't something the compiler understands. You'll still have a result value that you need to handle. Whatever operation you're calling still has the possibility of failing in general, even though it's logically impossible in your particular situation. If you can ensure by manually inspecting the code that you'll never have an error variant, it's perfectly acceptable to call unwrap. Here's an example. I see. So here we have the IP address, which I think we looked at once upon a time. And this is the variant where there's IP4 calling the home loop local host. Here they use parse and they use unwrap. The reason why they say it's okay to use unwrap here is because this will never fail. This is a static string that is hard-coded into our, binary encode. Thus, it cannot fail. Impossible. But the compiler cannot tell that. So we're creating a IP adder instance by parsing a hard-coded string. We can see that 127.0.0.1 is a valid IP address, so it's acceptable to use unwrap here. However, having a hard-coded valid string doesn't change the return type of the parse method. We still get a result value, and the compiler will still make us handle the result as if the error variant is a possibility, because the compiler isn't smart enough to see that this string is always a valid IP address. Yes, that is very true. I agree with that sentence, with the exception of the saying that the compiler isn't smart enough. Personally, I believe the compiler is smarter because it forces us to deal with it. No assumptions. Good compiler. If the IP address string came from a user rather than being hard-coded into the program, and therefore did have the possibility of failure, we definitely want to handle the result in a more robust way instead. All right. Continuing onward. Guidelines for error handling. It's advisable to have your code panic when it's possible that your code could end up in a bad state. In this context, a bad state is when some assumption, guarantee, contract, or invariant has been broken, such as when invalid values, contradictory values, or missing values are passed to your code, plus one or more of the following. The bad state is not something that's expected to happen occasionally. Your code after this point needs to rely on not being in this bad state. There's not a good way to encode this information in the type you use. Okay? So they're going to start giving us guidelines, or this is them giving us guidelines on error handling. And it's saying it's okay to panic when our code goes into a bad state or could end up in a bad state. And they define bad state as something that is extremely unexpected, seemingly, or something that you can't use in the following code, in the code following this error. If someone calls your code and passes in values that don't make sense, the best choice might be to call panic and alert the person using your library to the bug in their code so they can fix it during development. Similarly, panic is often appropriate if you're calling external code that is out of your control and it returns a invalid state that you have no way of fixing. So yeah, the second example here they brought up right here is when you're using somebody else's code that's external to your program and you have no way of fixing it because it's not part of your project. So you said panic. Let everybody know. Let the world know that something went wrong. However, when failure is expected, it's more appropriate to return a result than to make a panic call. Examples include a parser being given malformed data or an HTTP request returning a status that indicates you have hit a rate limit. In these cases, returning a result indicates that failure is an expected possibility and the calling code must decide how to handle. So what they're saying in this paragraph is that if you're ever writing code, which I guess we all do, but if you're ever writing code and that code has different scenarios that it goes through, and those scenarios can't possibly be failure, and it's fairly common or expected. For example, rate limiting. That's going to happen if you send too many requests. But if you send too many requests, you should expect to be rate limited, and thus you should handle the expected possibility of rate limiting. So that's what they're just saying here. It's just a small summary. When your code performs operations on values, your code should verify the values are valid first and panic if the values aren't valid. This is mostly for safety reasons. Attempting to operate on invalid data can expose your code to vulnerabilities. This is the main reason that standard library will call panic if you attempt an out-of-bounds memory access. Trying to access memory that doesn't belong to the current data structure is a common security problem. Functions often have contracts. Their behavior is only guaranteed if the input meets particular requirements. Panicking when the contract is violated makes sense because a contract violation always indicates a caller-side bug, and it's not a kind of error you want the calling code to have to explicitly handle. In fact, there's no reasonable way for calling code to recover. The calling programmers need to fix the code. Contracts for a function, especially when a violation will cause a panic, should be explained in the API documentation for the function. What they're saying here is that, one, you should always validate that the input that you're getting is valid for safety reasons. They were mentioning earlier about like the read out of bounds issue. I guess they said it was in C, where you have a vector or an array that maybe only has a length of 3, but you try to read at index 99. And in C, they brought up the example of C. It reads from what would be there. Like it finds a place where if this array did extend all the way to 99, it looks at that space and gives back the piece of memory there. That is read out of bounds. That is a security issue. But if this function that looked at the index, when it got the index input, if it realized that was an invalid value, then what they're saying is they should panic, which is what Rust does, at least for that example, when we did the vector 99. To be more explicit, they're saying that functions often have contracts of what is valid for use, or like what is valid input. And if a function calling this function were to send inputs that are clearly invalid, then panicking is okay. However, if you do panic, make sure to explicitly explain that in your API and documentation, or in your API documentation and whatever documentation you have. However, having lots of error checks in all of your functions would be verbose and annoying. Fortunately, you can use Rust's type system, and thus the type checking the compiler does, to do many of the checks for you. If your function has a particular type of parameter, you can proceed with your code's logic knowing that the compiler has already ensured you have a valid value. For example, if you have a type rather than an option, your program expects to have something rather than nothing. Your code then doesn't have to handle two cases of for some and none variants. It will only have one case, definitively having a value. Code trying to pass nothing to your function won't even compile. So your function doesn't have to check for those cases at runtime. Another example would be using an unsigned integer type of U32, which ensures that the parameter is never negative. What they're saying here is more or less just tooting their own horn. They're saying that you could they're saying that having verbose checks or having lots of error handling checks is annoying to write. But thankfully in Rust, we can rely on the type checker at compile time. So if you have a function that has a specific type or specific input, you're guaranteed that the compiler is going to check whoever's calling your code is calling it with the right parameters. I don't think there was really a need for them to mention it here because it doesn't apply to this language. But if you're writing in other types of languages, something more dynamic like Python, JavaScript, or Ruby, then you may have a lot more checks, or I guess you should have a lot more checks on your input just to verify that your input is valid, which includes types checks, which is the one they have here, like a type rather than an option. But that doesn't apply to this language. So moving on. Creating custom types for validation. Let's take the idea of using Rust type system to ensure we have a valid value one step further and look at creating a custom type for validation. Recall the guessing game in chapter 2 in which our code asked the user to guess a number between 1 and 100. We never validated that the user's guess was between those numbers before checking it against our secret number. We only validated that the guess was positive. In this case, the consequences were not very dire. Our output of too high or too low would still be correct, but it would be a useful enhancement to guide the user toward valid guesses and have different behavior when a user guesses a number that is out of range versus when a user types, for example, letters instead. One way to do this would be to parse the guess as an I32 instead of only a U32 to allow potentially negative numbers, and then add a check for the number being in range, like so. So just a summary, what we're doing here is writing a validator for this game that we wrote in chapter 2. Let's see how they go about doing it. So what they do here is we have the guess, which is the user input. We're going to make an I32 instead of a U32, which I guess made it only positive. Now it's potentially negative. And one way of checking it is to do a range. We can see that the guess is, if the guess is less than 0 or if the guess is greater than 100, tell them that they're doing something wrong. And then continue. Go through the loop and then guess again. That is one way of going about it, sure. The if expression checks whether our value is out of range, tells the user about the problem, and calls continue to start the next iteration of the loop and asks for another guess. After the if expression, we can proceed with the comparison between guess and the secret number, knowing that guess is between 1 and 100. However, this is not an ideal situation. If it was absolutely critical that the program only operated on values between 1 and 100, and it had many functions with this requirement, having a check like this in every function would be tedious, and it might impact performance. So what they're saying here is that this check, what they did here, yes, it works. It's good for this case. However, if we had many different functions that also had this requirement, then writing this line in all of them would, one, be tedious because it's just copying and pasting everywhere, and it could impact performance because it's extra work that the Rust has to do. So instead, we can make a new type and put the validation in a function to create an instance of the type rather than repeating the validations everywhere. That way it's safe for functions to use the new type in their signature and confidently use the values they received. Listing 9-10 shows one way to define a guess type that will only create an instance of guess if the new function receives a value between 1 and 100. Okay, so let's look at this. We're creating a struct, giving it a value. We have a new implement on the struct. We have a method called new, and it checks to see if the value is between 1 and 100. If it is not, it panics, and if it is, we return a guess, and you have your type guess. And then we have a value method, which is also public, and that you just call it and it just returns the value of what was passed in. Okay? So first, we define a struct named guess that has a field name value that holds an I32. This is where the number will be stored, yeah. Then we implement an associated function named new on guess. I guess they are called associated, but okay, yeah. Then we implement an associated function named new on guess that creates instances of guess values. The new function is defined to have one parameter, the value of type I32, and to return a guess. The code in the body of the new function tests value to make sure it's between 1 and 100. If value doesn't pass this test, we make a panic call, which will alert the programmer who is writing the calling code that they have a bug they need to fix, because creating a guess with a value outside this range would violate the contract that guess new is relying on. The conditions in which guess new might panic should be discussed in its public-facing API documentation. We'll cover documentation convention indicating the possibility of a panic in the API documentation that you create in chapter 14. If value does pass the test, we create a new guess and its value field is set to the value parameter and return the guess. The takeaway there is in chapter 14, we'll talk about documentation. And there are specific ways to label that your code might panic. Okay. Next, we implement a method name that borrows self, doesn't have any other parameters, and returns the I32. This kind of method is sometimes called a getter because its purpose is to get some data from its field and return it. This public method is necessary because the value field of the guess struct is private. It's important that the value field be private so code using the guess struct is not allowed to set value directly. Code outside the module must use the guess new function to create an instance of guess, thereby ensuring there's no way for a guess to have a value that hasn't been checked by the conditions in the guess new function. Alright, so what they're saying here is they're telling us what a getter is. So we go back to what this code does, right? So we define it as struct, right? But the value that's within the struct, called value, is private. The reason why it's private is so that once somebody has an instance of struct, we know that they cannot modify it or they cannot set a new value there. The reason why we don't want them to modify it is because we want to ensure that this value has gone through our check. And the way to ensure this value has gone through our check is to give the programmer calling or using our code only one way to giving them only one method of obtaining a guess instance, and that is this new function. This new function is going to take in a value, and it's going to have this check that they were mentioning, and this ensures that the value that guess have, that any instance of guess has passed this test. The reason why this is called a getter, which they were mentioning down there, is because the only thing that it does, it gets a value of something, the data that we already have stored here. Thus, it's known as a getter. Similarly, if you wanted to, I guess not in this case, in a different scenario, if you had a struct and you wanted to set this value, you could define a setter that changes it. And the setter function, the only thing it would do is set the value of, in this case, value. That's outside of this example. A function that has a parameter or returns only numbers between 1 and 100 could then declare in its signature that it takes or returns a guess rather than an I32. And would it need to do any additional checks in the body? So here's the guarantee that they were talking about earlier. So if we had a guess, given that guesses all have gone through the check, the value is always going to be between 1 and 100. We could put guess in our type signature. So in our function signature, we can put it there, or we could put it in our return type. And any code using a guess could know for certain that the value is always going to be within these bounds. Summary. Rust error handling features are designed to help you write more robust code. The panic macro signals that your program is in a state it can't handle and lets you tell the process to stop instead of trying to proceed with invalid or incorrect values. The result enum uses Rust type system to indicate that operations might fail in a way that your code could recover from. You can use result to tell code that calls your code that it needs to handle potential success or failure as well. Using panic and result in the appropriate situations will make your code more reliable in the face of inevitable problems. Now that you have seen useful ways that the standard library uses generics with the option and result enums, we'll talk about how generics work and how you can use them in your code. So yeah, that's the end of this chapter. Next chapter is generics. I hope that was entertaining. Hope you learned something. I did. Yeah. Good luck with your errors. Peace.